Hi, thanks for joining us for this video tutorial on ETX, our new powered loudspeakers from Electro. We wanted to tell you a little bit more about the key features and the really advanced technology that's built into ETX. It was really built from the ground up here in Burnsville, Minnesota by our engineering team, and really wanted to achieve best in class, best in performance powered loudspeaker, a great combination of brains and power. So we've got Ethan here, speaking of brains, and Ethan's gonna help me along a little bit with some of this really advanced stuff that's in this box. Now ETX, first and foremost, what stands out to me is the amazing DSP that's in this box. We're running FIR drive. Can we explain that to the folks at home a little bit?
Yeah, absolutely. FIR drive is the name that we give to our system designs that integrate advanced signal processing for filtering, for optimization, for system protection, as well as the design process that goes into actually creating the algorithms, measuring the loudspeakers, and really creating the ultimate performance. And there's a variety of different elements that go into FIR drive. There is the FIR filters, which we can't really begin to discuss until we start talking about IIR filters. A traditional IIR, or infinite impulse response filter, is what most people know when they've worked with parametric equalizers. It's a signal processing algorithm that's really designed to emulate analog filters. And they're great. They sound okay, they're comfortable, people are familiar with how they operate, and they don't take a whole lot of signal processing to actually implement. The downside to an IIR filter is they carry along some of that baggage that you get with analog filters as well. You've got limited types of filters that you can implement, you can get limited amounts of resolution, and whenever you're making an adjustment with an IIR filter, you're adjusting both magnitude as well as phase. So balancing those things out can be a bit of a challenge with a traditional filter. Now, conversely, a FIR, or finite impulse response filter, takes a lot of those restrictions and kind of throws them out the window. With an FIR filter, we can create pretty much any filter type or shape that we need to really achieve proper optimization of the loudspeaker in the cabinet. So we can address all of the nonlinearities and all of the dips and peaks and valleys and things that you see in a raw transducer to really deliver the ultimate performance out of that loudspeaker configuration that you're going to see inside of the cabinet.
So if I understand it right, if we're talking about IIR, or the older way of doing things, if you were to adjust maybe a boost or a cut on any given frequency, that would have a tendency to affect other frequencies, where with FIR, we're getting a little more linear, and if we want to shape the EQ, we can get much more precise and really just affect what we want to rather than other things around it?
Yeah, that's a big part of it. One of the things that FIRs make possible is the fact that we can create very, very steep filter curves. So there's minimal overlap between the two components that reside inside of the loudspeaker.
So the components end up doing exactly what they were designed to do, and
exactly
that's
right.
it. They don't have to do more. That's very cool. So beyond FIR now, our FIR drive also includes some protection.
Absolutely.
Peak anticipation limiting.
Yep.
What is that?
Well, when we start talking about loudspeakers and when things can go wrong, it's really important to understand the different types of failures that you could see in transducers before you actually go back and look at how you can begin to address those. So FIR drive actually includes two different types of limiters, and I'll talk about each of those independently. The first one is what we refer to as a peak anticipation limiter, which is designed to protect against mechanical failures, whereas the thermal energy management and protection limiter, or temp limiter as we call it, we try. This algorithm is really designed to protect against thermal failures. And I've got a couple of examples here to show you what some of these different failure modes look like. I'm going to advise sensitive viewers to avert your eyes because you're going to see some horrible, horrible audio failures. So here are a couple of examples of where transducers go bad. This first example here is a classic example of a mechanical failure. And what's happened here is too much voltage has been applied to this device. And those are the type of things that you can see if somebody drops the mic, if you get a real sudden pulse of audio through the system, anything that produces an instantaneous pulse that exceeds what the loudspeaker can actually handle.
Over-excursion.
Exactly, and that's what's happened here. You can see this loudspeaker has basically blown itself apart because it's had too much energy actually applied to it, too much voltage, and yeah. It's no good. So the way we can protect this is through what we refer to as the peak anticipation limiter. And this is a really tightly designed algorithm that not only protects the loudspeaker from these type of mechanical failures, but it eliminates some of the issues that you find with other types of limiters. A lot of times when you're getting very heavily into gain reduction with these type of algorithms, you can begin to develop sonic artifacts. You'll pick up harmonics and other types of transients and noise that can be generated by the algorithm itself. The peak anticipation limiter was designed to operate not only in a look-ahead manner, so it can stop those peaks before they actually get through and can do this kind of damage, but it was really designed for sonic excellence as well. So it's a very clean, very smooth, virtually inaudible algorithm that comes in as you begin to go into gain reduction when you need that type of protection.
Okay.
So the peak anticipation limiter is designed to respond to short, quick, instantaneous bursts. It acts very quickly, shuts down that signal from actually getting through and doing damage, and then you can move on with your show. The other type of failure that you can get is kind of at the opposite end of the spectrum, and that's where this little beauty comes in. This is a great example of a thermal failure. And whereas a mechanical failure occurs when you have too much instantaneous voltage hitting that device, this occurs when you have too much power that's actually being applied. And these two things can actually begin to feed on each other, because what can happen is as I'm feeding my audio into the limiter algorithm, I'm going to start getting more and more into gain reduction. And that crest factor of my audio signal is going to begin to get lower and lower and lower. So all of a sudden my RMS power that I'm feeding the woofer increases and goes up and up and up and up and up. And what will wind up happening is you'll begin to start to actually heat up the voice coil. And this is a great example of what's happened when something's gotten a little bit too hot and has basically blown itself to pieces. So the way we're able to manage this is a bit different than a typical RMS limiter, where you just apply an across-the-board cap on how much RMS power you can provide. The temp limiter actually runs an algorithm inside of the signal processing that will simulate the thermal behavior of the voice coil with the amplifier and the power signal being applied. So we can look at very long-term characteristics of what that signal is actually doing and make very small adjustments to keep the thermal characteristics of the transducer under control. And again, this is one of the great advantages that we have since we design all of these components. We know exactly what those characteristics of those voice coils and those transducers
we know
are
where
going
the
to be.
breaking point is.
Exactly. So we can control all of that. And what we found in our studies is you have a very logarithmic rise in temperature when you're getting to that breaking point of the loudspeaker. And when you're kind of at that critical edge, a change of as little as 1 dB can actually equate to a 50°C change in the voice coil. So very small adjustments can make enormous differences. And what the temp limiter will actually do is run that algorithm to simulate the thermal characteristics and behavior in the transducer and make very minute adjustments over long amounts of time to keep those thermal characteristics under control. So what that means is it's virtually inaudible. Even a 1 dB change in that signal strength can save your transducers. So you don't hear this coming into action. It just goes in, it's very smooth, it's inaudible, and with the combination of the temp limiter and the PA limiter, we're able to protect against the mechanical damage as well as the thermal damage.
If you have any questions and you want to learn more about this, you can call the phone number just below here or visit us at electrovoice.com.